Buedeker, pointing this out, found furthermore that both of these effects are first order in the magnetic field. So you can't simply take the limit of small b and get rid of one of them. And in fact, in the regimes he was interested in, the alignment effect was much bigger than the precession. So he said, look, there seem to be two components, theta and phi, or theta z and theta y, he called them. What should I do? And he just decided to add them in quadrature and look at the full three-dimensional rotation angle. I don't think there's any great justification for doing that. I think he liked it because it gave him a result he had other reasons to believe. And he said, well, let's be optimistic and take that as the right answer. The interesting thing is that there were other approaches that also gave two different times. In particular, one due to Sokolovsky and Baskin, which involved Feynman path integrals and gave a complex number, as Feynman path integrals always do. The interesting thing is the real and imaginary parts of that complex number correspond precisely to the two angles we see here. Except at the time, no one knew what to do with complex times or real and imaginary parts. And I would argue that now we do understand what to do. Based on the weak measurement formalism of Aharonov, Albert, and Weidmann, which was published a few years after this Larmor clock work, we understand that the real part of what I call a weak value, in this case, the precession angle in the XY plane, corresponds to the effect of the system on the pointer, the expected change in a pointer position, a classical measurement result, in other words. While the imaginary part, which here corresponds to the tendency to align with that magnetic field, is something purely quantum that really has to do with the back action of the measurement. It doesn't tell you so much about the sensitivity of the pointer to what the system is doing. It tells you rather about how sensitive the system and its post-selection are to the interaction with the pointer. So to separate all these things, it's not enough just to measure one angle. We needed to do full tomography on the spin. And Ramon and David figured out how to do that. And here are pictures along the Bloch sphere at very high velocities. We began along the x direction. We spend very little time in the barrier, so the spin ends up almost along the x direction. But as you lower the velocity, the particle spends more and more time interacting. You see more and more precession angle, but also more and more alignment. Here in the xz plane, you see that the lower the energy of the particle, the more you tend to align with z, but also the more you tend at first to precess towards y. So we can summarize all those data. I'll apologize in advance for a very busy plot. Versus velocity of the incident particle, where about 5 millimeters per second here is the barrier height, we can plot both the in-plane, or real time, and this out-of-plane, back action time. And I've compared them to a few theories, but there's an experimental complication, which is that our wave packets still have some width in velocity. And the transmission is much larger, of course, at higher velocities. So if we send in a wave packet centered at 4 millimeters per second, what actually gets transmitted is not the stuff at 4 millimeters per second. It's the stuff off in the Gaussian tail around 4.5 millimeters per second, but that had a much higher transmission probability. So that's why from these ideal theoretical curves, like the solid green line for the Buedeker-Landauer semi-classical time, we get a smeared out version, in this case, the dashed green line, which does not diverge as quickly because you're always really biased towards a slightly higher velocity. And the same thing is true for our weak measurement predictions for the in-plane and out-of-plane times. What do we actually see qualitatively? If we look at that in-plane time, we see it grows. It does not diverge, of course. It doesn't grow as quickly as the Buedeker-Landauer semi-classical time. And it seems to start dropping again at lower velocities. As you see, that's about a 1 sigma effect here. We have more recent data that I'm not showing that really nail that down, and we'll be submitting a paper shortly demonstrating that effect. And we see the out-of-plane time, the thing that shouldn't even exist classically, that up here in the classical regime goes to 0, but once you're in the tunneling regime, begins to grow. So we really confirmed that these weak value times are believable, and they behave in more or less the way that we expected them to. Now, as excited as we were to see that, I mean, we really had been working towards this on and off for 20 years. it just confirms a theory that I at least thought I knew quite some time ago. And it doesn't look that different, to be honest, from the group delay time that our group and others have already measured. What I think it really opens up is the possibility to ask deeper questions about the history. And here's the one we're working towards now. Don't ask how much time did the atom spend throughout the barrier. Ask how much time it spent just in this yellow region, or in this region, or this region, or this region. And find out, do transmitted and reflected particles have different histories? Here's the intuition. As thick as I make the barrier, eventually the reflected particle doesn't care. It was probably reflected in the first evanescent decay length. So you might expect that reflected particles never see anything other than the entrance of the barrier. While a transmitted particle, I know it came in from the left and I found it on the right. Shouldn't I conclude that it spent time everywhere along that path? Interestingly enough, if you do the calculation, that's not quite what you find. This red curve shows what we predict for the reflected particle, which is basically just psi squared. Almost all the particles are reflected, so there's almost no difference between asking about the reflected particles and asking about the whole wave packet. But if you ask, again, using this weak measurement formalism, but that's the correct way to predict the results of our experiments, what would happen if you look only at transmitted particles? You do get a symmetry. You have just as much information from the initial condition that it came in from the left as from the final condition that it exited on the right. But what you see is an exponential decay on the left and an exponential growth on the right, with essentially 0 time spent anywhere in the middle of the barrier. So once more, we raise this puzzle. How do particles manage to get across a barrier without spending too much time there? It seems as though the particles spend some time getting in and then spend some time getting out, but it doesn't care how much is in the middle. And we still find that very mysterious. And I'd like to have a deeper picture of that. But mostly I'd like to verify this experimentally, really do the first measurement where we can demonstrate clearly that depending on the final state of your system, you have gotten more information about the history. You've learned whether or not it spent any time in this region over here. There's one caveat I'll mention, which is that here I'm only plotting the real part of the time, the in-plane precession, because I think that's really the right one to be asking about when you ask how much time did it spend. However, we've also calculated the imaginary part, and if you do that, you find it's essentially constant across the whole barrier. That just tells us something we know, which is that perturbing a barrier lowers the exponential transmission probability for the particle. And it doesn't matter where I add a little extra height to the barrier, it has the same effect. If you think about the WKB approximation to the transmission probability, that's very, very easy to see. But I would say that's telling me that the particle is equally sensitive to every region in the barrier. That's not the same as saying that a probe at any region in the barrier would be equally sensitive to the particle. Every time I even say that, I know it sounds confusing. And maybe that's the most basic lesson from tunneling times, which is that in order to answer a quantitative question, like how much time does a particle spend in a region, we need to turn it into an observable. And the way we do that is not by going to a textbook and asking what's the observable. It's by thinking about physics experiments and saying, what do I mean by a measurement of this quantity? And then writing down the Hamiltonian that describes that coupling to see what is the mathematical object that represents the measurement. Normally, however, we assume that a quantity that we can measure many different ways classically, like the position of an electron, really is a fundamental quantity. And it will have the same value no matter how I measure it. It turns out for time, which is not represented by an operator in quantum mechanics, and certainly not the time spent in a barrier, there are many different things you could imagine measuring classically that give the same result. And once you go to the quantum regime, there is no longer that guarantee. They're not necessarily giving you the same result. So what we've learned is just that there's a kind of coincidence. There are different observables that become equal in the classical regime, but they really have different physical meanings. So we need to learn, what are these different timescales? What are they describing? How would I measure each of them, and what are their values? Okay. So we're trying to set up to do that experiment. We're not quite there yet, but there's a really interesting spin-off that I also hope we can do in the lab, which began long ago when this was just, a pipe dream, but I was describing the proposal at a conference, And Bill Phillips said, why do you keep talking about this limit as b goes to 0 or making weak measurements? Why not just strongly measure whether the particle is in the barrier or not? And I very glibly said, well, if you strongly measure whether the particle is in the barrier or not, whenever you find it in the barrier, you, so to speak, collapse it to a wave packet inside the barrier, which automatically has enough energy to exist under that potential, or above that potential, I should say. And therefore, once you find it there, you've created real momentum components that can roll across the rest of the barrier without even needing to tunnel. So the prediction was that if you could strongly measure that a particle was in the barrier, even if the barrier was so thick that you'd been seeing no tunneling before then, you might still find it in the first exponential decay length. Whenever you did that, it would become essentially equally likely to be transmitted or reflected. So you could enhance tunneling by the mere fact of looking for particles inside the barrier if you look for them strongly enough. Now, we didn't really know how to look for them strongly enough. We imagined taking this probe, putting it at the beginning of the barrier inside the first exponential region, and making it so big that it did something like a pi pulse. Except I don't really know what that means. I don't know how to do that because we didn't know how long the particle is spending there. How do you tune something to be a pi pulse if the time itself is an unknown to begin with? So here was our more recent idea. Just last year, we started thinking about this. What if we stick with the small magnetic field, what I was calling a weak measurement before? We lower the strength of that probe, so there's only a very small rotation angle. But now I post-select. I post-select on the spin of this electron or atom. I only look at cases where it comes out along the minus x direction. So remember, it began in plus x. It only saw this field if it was in the barrier. There's no way I could ever find it orthogonal to its initial spin state unless it interacted with that field, and therefore unless it was inside the barrier. So there was our conjecture. Have a weak magnetic field confined to the barrier, and then look only at the minus x spin component, and that should be equivalent to having determined with certainty that the particle was inside the barrier. Will that then enhance the transmission probability? By which I mean, is the transmission amplitude for the minus x going to prove to be equal to the reflection amplitude for the minus x? So my student David Spearings simulated this stuff, and he found that my conjecture was incorrect. This doesn't happen, and the simple way to understand that in retrospect is that this time-independent probe can't change the particle energy. So there's no way that this could give the particle enough energy to traverse the barrier. And in terms of this collapse picture, what it means is that measuring that the particle was in the barrier at some unspecified point in time doesn't collapse it. That's not even a projection operator. It doesn't have eigenvalues of 1 and 0. It's a time integral of a projection operator. So here's what he found. Do the simulations. You look at this ratio of the transmission and reflection probabilities for the particle that ended up with the minus x spin. And on a log plot, you see that it's always exponential. It's exponentially more likely to show up on the right if the position where I put the probe, where I found the particle, is on the right. It's exponentially more likely to come out on the left if the position was on the left, which is really funny because what it means is it looks as though the particle shows up at this position where I found it, but it still needs to tunnel either to the right or to the left. And it has an exponentially decaying probability in either direction. It turns out, mathematically, it's easy enough to show why that occurs, but it's kind of provocative.